middle can be determined from this equation. So measure how fast something near it is moving if it's moving around in a circle like this, and you measure the mass of this. Okay? So if you know these other things, you can quickly determine the mass of the sun, for example. You know how fast the Earth moves, you know the radius of its orbit. It takes a year to go around. Look it out, and just measure the mass of the sun. Okay? This works great if you know that the object's actually going around in a circle. But imagine that the circle it's going around is big enough so that it takes 1 billion years to go around. You can't wait 1 billion years to find out whether it's really going around in a circle. So all you do instead is you get a picture at one moment of its velocity, and you don't know if it's going around in a circle. So you have to make some kind of assumption. In cases where the time of observation is longer than the time it takes to go around, this is great, because you watch it go around and you can figure out exactly what mass is present. So this was used a lot in the 19th century to discover things that had not been seen. They weren't really dark matter, they were invisible things. And the first of those was the planet Neptune. So astronomers in the early 19th century mapped out the motion of all the other planets. And they knew how they should move because of Newton's theories. And what they found is that Uranus, in particular, moved a little differently from what it was supposed to. And that told them that something they didn't know about was tugging on Uranus. And believe it or not, with no calculators and no computers, they were able to work out what it was that was tugging on the planet. And say, there needs to be another planet right there. And they looked, and they found it. Right? So this gravitational detection of something invisible was first done with Neptune. It was later done to show that some stars are binary stars. So you would look at a star and you would see that star getting tugged around. The way you would see it is you would see it moving toward you and away from you. Remember, you could measure the velocity of something. So you could see it moving toward and away from you. Like, wait a minute. Stars don't move toward and away from us unless something's tugging on them. And the thing that was tugging on them was a companion. Because they were going around each other. It would come toward you and away from you, and toward you and away from you. It was in orbit. Okay? So we discovered those kinds of binary stars. This gave us accurate stellar masses. It let us prove that black holes and neutron stars existed. Because we don't see the light very easily from black holes and neutron stars, but we can see them tug on their companions, which are often visible stars. So lots of ways that this can happen. This is currently being used to detect planets very regularly. When I was your age, we knew of no planets outside the solar system. None. All right? The first planet outside the solar system was detected in 1995. And since that time, we've detected many thousands of planets in other solar systems. And we now know that most stars host systems of planets around them. It's a huge change, right? Especially if you're interested in aliens. I mean, honestly, it's true that we always expected there were planets around other stars. But we really didn't know until very recently. And we're just at the beginning of understanding those planets in the solar system. So this is a powerful approach. It has this drawback, though, that if you don't know the object's going around in a circle like that, you can't be sure. I mean, maybe this object is just flying by, right? Maybe the gravity of this is almost nothing. And you measure that velocity, right? So you have to be very careful about using this method. It's much less useful when the scales are much bigger than the solar system. Let's see if I can make this work. This is a particularly interesting example of watching the effect of gravity from an invisible object on the motion of stars. Let's go back up there and see if I can make that work. I'm sorry I can't do that. I will share with you the video of this. It is the case that we now watch stars moving near the center of our galaxy, very, very close to the center of our galaxy. And we see them being tugged incredibly hard. So over a period of about 15 years, you can watch these stars fall in and speed up and speed up and speed up and zip around and then come back out. And we can tell there's a very massive, invisible object sitting right at the heart of our galaxy. It's a supermassive black hole. And we know it's there because we watch these stars go in these orbits and zip around the center of the Milky Way. And it takes 15 years to observe them. We've done that. So that's another way of seeing dark matter in this kind of thing. So if the time of observation, though, is a lot less than the time it takes things to orbit around, this is a lot harder to do. But I do want to tell you about it, because this is what led us to first understand that there was dark matter. A really fascinating man named Fritz Zwicky in 1933 was looking at an object called the Coma cluster of galaxies. And let me show you a picture of Coma. You see all these whitish galaxies? You can see maybe 40 or 50 here. There are actually thousands of galaxies in the Coma cluster of galaxies. What is a cluster of galaxies? It's a whole grouping of galaxies in three-dimensional space, like a cloud of galaxies. They are held together by their collective gravity, because each one of them is moving. They fall in toward the center, and then they zip around, and they go out, and they get tugged back toward the object by the collective gravity of it, and then they fall in again, right? It's a swarm of galaxies, held in place by the collective gravity, the collective mass of all those galaxies, right? That's what holds it together. When Fritz Zwicky went and measured the velocities of all these galaxies, remember, if they were moving really fast, they would go toward the center of this cluster and zoom right through it. And the gravity wouldn't be enough to slow them down. They'd keep going. So when he measured how fast they were going, he was astounded, because they were moving way too fast. They were moving so fast that it looked like the whole object was blowing apart. But there it was, sitting there. And it didn't look like it had just come from an explosion. So he had to ask himself, maybe it weighs a lot more than I think it does. Because if it didn't, it would have blown apart already. Now, I couldn't be sure, right? Because he just gets a snapshot. He doesn't get to watch it for billions of years. But it gave him this hint that maybe a cluster of galaxies was 100 times more massive than it seemed to be. All right? So that was what Fritz Zwicky did with the Coma cluster of galaxies. Later in the 1970s, a very important astronomer named Vera Rubin did the same kind of things with galaxies. You know, a galaxy, take a typical spiral galaxy, it's rotating around, right? So the stars at the outside, they're held into the galaxy only by the gravity of the galaxy. Otherwise, those stars would just go off in a straight line and fly away. So they're held in by this galaxy so that they rotate around it. If the galaxy is really massive, then they could be moving really fast and still be held onto by the galaxy, right? So what Vera Rubin did was to measure how fast galaxies are rotating from their center, moving out to the edge. And what she found is when she got to the very edge of the galaxy, they were still moving super fast. They were moving so fast that it looked like the galaxy must be embedded in a huge cloud of matter that you couldn't see. A dark matter halo around the galaxy. So just to show you what that looked like, they would measure these rotation curves. And this is showing you the velocity of things going around, the stars going around, as a function of distance from the center of a galaxy. The velocities, you notice, are measured in kilometers per second. Stop and think about that for a moment. 200 kilometers per second is how fast stars move in galaxies. Very fast, right? And we're not talking about a little thing moving very fast. We're talking about a star moving that fast. It's an enormous amount of energy in it. And what she found is that the rotation curves of galaxies, the speed of stars as a function of distance from the center, would rise and then would flatten all the way out to the visible edge of the galaxy. And the only way that could happen is if the galaxy was filled with a cloud of what she called dark matter. And that dark matter would have a density that was pretty small in the center, but then would rise toward the edge. So it became the dominant thing. At the edge of the galaxy, there was more dark matter than stars or gas. And that's what you needed in order to explain the data that Vera Rubin saw. In the early 1970s, she saw this. So there are lots of limitations to the way you use this kind of method, but it's what gave us these ideas. So just to give you a sense, I don't know, we have a little too much light from the windows, but this is a spiral galaxy, and she would start at the center and measure out to the edge. And then there's nothing more to measure farther out. You couldn't see any more light. So she couldn't really tell how fast the rotation curve was out there. But it was another really powerful reminder that there might be a lot more matter in the universe than we thought. By the time I started working on this in the 1980s, people were pretty convinced there was a problem here, but they had no idea what it was. And since then, what we've been able to do is make more and more and more measurements of this to show us that this invisible matter seems to be kind of everywhere. So these results all suggested the presence of something with mass that doesn't emit or absorb light. Okay, that was Newton's method, the dynamical method. The part that I've worked on is mostly Einstein's method, what's called gravitational lensing, or looking at the bending of light. So again, just to give you a sense of how this works, if you have a massive object and a ray of light passes some distance away from that massive object, that ray of light will be bent. It comes in this way, it goes by the object, it gets bent. And it goes out another way. All right? So let's think about, and you can see that those things depend on the mass of the object and this geometry here. So what might happen if light is bent? Imagine an object that's actually sitting right here. That object sends light out in every direction. Some of that light goes over here, and we would never see it, because we're the observer over here. Some of that light goes over here, and we would never see it. Some of it heads off in this direction and gets bent by this massive object. And we see that light coming to our eye from this direction. So when we look at it, we see the object here. That's where the light seems to come from, even though it's there. Think about a mirror. If there were a mirror on the wall there, you might look in it and see me in the mirror. Because some of the light from me would bounce off the mirror and come to you from there. So when you look back, it would seem like I was there. Right? Just like that.